Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at applications of both trigonometry and similar triangles. So let's start with similar triangles. A very common application of that is using shadows to estimate the height of things. So Austin is 1.6 meters tall, casts a shadow of 2.4 meters. Same time of day, a tree casts a shadow of 13.5 meters. We're going to calculate how tall the tree is. So whenever you're given a worded question like this and you're not given a diagram, first draw a diagram. So that's what we're going to do here. So Austin is 1.6 meters tall, casts a shadow of 2.4 meters. Same time of day, a tree casts a shadow of 13.5 meters. How tall is the tree? So if you are given a worded question and no diagram, first draw a diagram. So we'll have Austin here, 1.6 meters tall, and he casts a shadow of 2.4 meters. So at the same time of day, we have this tree over here. We don't know how tall it is. It casts a shadow of 13.5 meters. How tall is the tree? So what does this have to do with similar triangles? Well, we just make these into triangles like this. So why would these triangles be similar? Well, when we're talking about height, we always mean perpendicular height. So if Austin's 1.6 meters tall, that's obviously his height when he's standing up straight. And it'll be the same for the tree. We're going to find its perpendicular height. That's what we mean when we say height. But that's not enough to show that they're similar. If we're talking at the same time of day, the angle that the sun makes with both of them will be the same. The sun will be up here, but it will make the same angle with Austin and the tree. So this angle here and this angle here will be equal. It's not like the sun's going to hit Austin at a different angle than it hits the tree. So now we have two triangles. They have two pairs of equal angles. They're similar by the AAA test. So that helps us because they're similar, we know that sides will be in the same proportion. So this side and this side, they correspond to each other because they're the sides touching the angle theta and the right angle. So we can calculate the scale factor really simply. Side in the larger shape divided by the corresponding side in the smaller shape. So that is 5.625. Again, the scale factor means each side in this larger triangle is 5.625 times its corresponding side in the smaller triangle. So to find the height of the tree, which I've called T, because it's in the larger triangle, remember we times. So T is just going to be its corresponding side times the scale factor. And putting that on our calculator, we get 9. So the tree is 9 meters tall. Let's look at a harder question involving similar triangles. So similar triangles can actually be used to calculate something like the width of a river. That would be very hard to measure just using like measuring tape or whatever. So what you can do is you can plot, say, a rock here and a rock here and measure the distance. So let's say the distance between these was 4 meters. Then you put a rock here and a rock here, you measure the distance. So let's say the distance here was 10 meters. So let's say I measure the distance here and it comes to be 6 meters. So just by measuring all of these distances here, I can calculate the width of the river. So the width of the river is this length here, x. So what I have here are two right-angled triangles. So they are similar because they both have a right angle and they have a common angle here. Doesn't matter what it is, it's in both triangles, so it must be equal. So once again, by the AAA test, these two triangles, small one and big one, are similar. So we can easily calculate the value of x. So the scale factor is easy to calculate. It's just side in the larger shape over corresponding side in the smaller shape. Scale factor 2.5, each side in this large triangle is 2.5 times its corresponding side in the smaller triangle. So the side in the smaller triangle is x. So that, if I multiply it by 2.5, I'm going to get the side in the larger triangle. The side in the larger triangle is x plus 6. So this is just a little bit harder because we have this tricky equation to solve. But it's still doable. We know how to do this. We've done it before. So if I want to solve this equation, because x is on both sides of the equation, I subtract the one with the lowest number in front of. This one has a 1 in front. This has a 2.5. I subtract x from both sides. So 2.5x minus x gives me 1.5x, and that equals 6. X and minus x cancel each other out. So now to find x, instead of timesing by 1.5, I just divide it by 1.5 and I get the answer 4. So the width of the river is 4 meters, which we figured out using similar triangles. Let's now look at some applications of trigonometry. So we're going to do a couple of examples involving angles of elevation and depression. So let's look at this question here. The angle of elevation to the top of a building from a point 40 meters away is 13 degrees. How tall is the building? So once again, we're not given a diagram, so we're going to first draw a diagram. So we've got this building over here, and we're talking about a point 40 meters away. So the angle of elevation is the angle made with the ground when you're looking up at something. So it means the angle of elevation is actually this one here, 13 degrees, made with the ground looking up at the top of a building. So we can assume that a building is at right angles to the ground. I can easily calculate the height of the building. I'll call that x. Because I have a right angled triangle, I can just use trigonometry. So the point is, if you wanted to measure the height of a building, that's not easy to do. It's easy to measure how far you are from the building, and actually measuring the angle of elevation to the top is simple. You just use what's called a clinometer. So I can calculate x really simply here. So I have a right angled triangle. I have the side opposite the 13 degree angle and the side adjacent. So I use tan. So I get tan 13 equals opposite over adjacent. The thing I want to find is on top, so therefore I multiply each side by 40. So x will just be 40 times tan 13. I just put that on my calculator, and to 2 decimal places I get 9.23 meters. So the height of this building would be 9.23 meters. So trigonometry made this problem really easy to solve. Now we're going to look at angle of depression, which is the angle when you're looking down. So let's do this question here. 2 swimmers on the same side of a cliff. The angle of depression from the top of the cliff to the swimmers, 33 degrees to one of them, 42 degrees to the other. The cliff is 30 meters high, and we're going to calculate how far apart the 2 swimmers are. So once again, we're given words but no diagram. Let's draw a diagram. So what we have is some 30-meter cliff. And we've got 2 swimmers over here. So we'll put them there and there. So this one's talking about angle of depression. So that's the angle with the horizontal when you're looking down. So I'm at the top of the cliff looking down. So the angle to one of them is 33 degrees and the other is 42 degrees. Now, the angle of depression is made with the horizontal. So I'm going to draw a horizontal line here. So for one of them is 42 degrees. So that means this angle there is 42 degrees. To the other is 33 degrees. So that means this angle here is 33 degrees. We want to find how far apart they are. So we want to find x here. So what we need to do is we need to come up with a right-angled triangle, because we can only use trigonometry. We only know how to use it so far in right-angled triangles. So here we sort of have 2 right-angled triangles, this one and this one here. And we can use those to find x. So this is similar to the harder question I did in the finding sides video. So the angle of depression is the angle looking down, but it's always equal to the angle of elevation. So this angle's 42, this angle here must be 42 degrees. So the angle of elevation looking up from this swimmer is 42 degrees. And the angle of elevation here would be 33 degrees. The angle of depression and angle of elevation is always the same. That's actually because these two angles are alternate, these two angles are alternate, which we did in a previous lesson. So if I want to find x, well, x is not in either of the right-angled triangles. What I'm going to do is I'm going to find this length here in the big right-angled triangle, this length here in the smaller right-angled triangle, and subtract them, and I'll be left with this distance here. So let's start with this distance here. I'll call that z. So to find z, this side here, it's adjacent the 33-degree angle, and we have the opposite. So once again, we're using tan. Tan actually comes up a lot in angles of elevation and depression questions. So we have tan of angle equals opposite over adjacent. So the thing we want to find is on the bottom, we need to divide. Z will be 30 divided by tan 33 because it was on the bottom. So that gives us approximately 46.1959 meters. I'm putting a lot of decimal places here because I need to use this later. I need to subtract this distance from that number. So now I'm going to find this blue distance here. I'm going to call that y. So y is in the smaller right-angled triangle. So y is again the adjacent, and we have the opposite. So this time it's tan 42. Tan, because it's opposite and adjacent, equals opposite over adjacent. So y, again, we divide because it's on the bottom of the fraction, the thing we want to find. So I just put 30 divided by tan 42 on my calculator. So the answer I get here is about 33.3184. So this distance is 46.1959. This is 33.3184. So this is just that minus that. So I'm left with x is 12.8775. So x is about 12.88 meters, and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.